Welcome back. In the last session, we have seen a different proof of Bezout's identity. We showed that given all possible linear combinations of two positive integers a and b, we can find GCD in that set as the least positive integer in that particular set of all linear combinations, the set of all positive linear combinations in fact. But previously, using Euclidean algorithm, we saw that we can write GCD of a and b d as a linear combination of a and b by finding concrete x and y. Therefore, the Bezout's identity proof using Euclidean algorithm can be probably termed as a constructive proof, where we are finding concrete numbers x and y in such a way that d equal to ax plus by, whereas the proof that we had in the last session, where we just saw that the GCD of two integers a and b, two positive integers a and b, is the least among all the positive linear combinations ax plus by. So we have two types of proofs. One is just an existence proof, where we say that there exists x and y such that d is equal to x plus by. In the first one, using Euclidean algorithm, that is a constructive proof, where we are finding two concrete x and y in such a way that d is equal to plus y. Now, the importance of the proof, which is the non-constructive proof, the existence proof, is that the property that d is the least positive integer among all possible linear combinations of a and b, we are going to make use of that interesting fact for discussing a few problems. We are going to discuss actually some consequences of not just Bezout's identity, but consequences of the proof that we have seen for establishing that d can be expressed as a linear combination of b. Our first question in this sequence of consequences is the following. Let a be positive integers, c a positive integer. So we have three positive integers a, b and c. Question is the following. So that GCD of AC and BC, that means a and b both are multiplied with c, is the same as c times the GCD of a and b. This question seems to be somewhat a trivial thing, but it is not actually so, and we are going to make use of the proof of Bezout's identity that we saw in the last session. Okay, so according to the proof that we have seen for showing that d is a linear combination d, where d is the GCD of a and b is a linear combination of the form ax plus by, we constructed a set consisting of all am plus bn, where am plus bn are integers with m and n varying throughout integers, and then we took the positive integers from that set, and d we derived to be the least positive integer in that set. So we are taking a clue from that particular proof. We have, if d equal to GCD of AB, then d is the smallest positive integer in the form am plus bn, where mn integers. So GCD of a and b is nothing but it's the smallest positive linear combination of a and b. Okay, this is the most important thing that we are going to make use of. Therefore, what about the GCD of AC and BC? AC, BC, GCD is the smallest positive integer in the set of all ACM plus BCN, where m and n varying throughout integers. So we have to find the smallest positive integer in the set ACM plus PCN, and that will be the GCD of AC and PC. Now, ACM plus PCN, this is nothing but this is equal to C times AM plus PN. In this expression, what are the fixed numbers and what are the possible variables? We know that C is given, therefore this is fixed, we cannot change it. A is given, we cannot change it. B is given, we cannot change it because A, B, C are all given in the question. Now, what are the things that we can vary? So M and N we can vary. Now, we have to vary M and N in such a way that C times AM plus BN is least. Now, C times AM plus BN is least if AM plus BN is least. Because C is a fixed number, there is no possibility of varying it. So we have to vary M and N in such a way that AM plus BN will be the least positive. But what is the least possible value of AM plus BN? But least positive integer AM plus BN is D. Therefore, least positive value of C times AM plus BN is nothing but C times the least positive value of AM plus BN, that is nothing but CD, equal to C times GCD of A. That's it. So we are proving this result, we are establishing this result not using the Bezout identity directly, but in fact using the fact that D is the least positive linear combination of A and B. Now we have another interesting problem. Two positive integers A and B are relatively prime if and only if there exist integers alpha beta such that A alpha plus B beta equal to 1. Prove this. So we have to show that if A and B are relatively prime, then we have to find alpha and beta such that A alpha plus B beta is equal to 1. And on the other hand, if there exist alpha and beta integers such that A alpha plus B beta is equal to 1, we have to show that A and B are relatively prime. Okay, suppose that we have to verify two statements. We will show that first, if A and B are relatively prime, then A alpha plus B beta is equal to 1. That's very easy. Suppose GCD of AB is equal to 1. That means A and B are relatively prime. But what does Bezout identity say? Bezout identity says that GCD can be expressed as a linear combination of A and B. So 1 equal to GCD of AB equal to linear combination of A and B. There exists alpha, beta, Z such that 1 equal to GCD of AB is equal to A alpha plus B beta. So this is established. So if GCD of A and B is 1, then A alpha plus B beta is equal to 1. There exists some such two integers alpha and beta. Conversely, suppose there exist alpha beta integers such that A alpha plus B beta equal to 1. Now, what is the GCD of A and B? GCD of A and B is the least positive linear combination of A and B. But what is the least positive linear combination of A and B? The least positive integer, we know that it's the first natural number 1. So GCD of AB is the least positive linear combination of A and B. Therefore, we have to take all possible An plus Bn and find the least positive integer among that. But already it's given that there is an alpha and beta such that A alpha plus B beta is equal to 1. So what is the least possible linear combination then we have? So that is equal to A alpha plus B beta is equal to 1. Therefore, GCD is going to be equal to 1. Therefore, GCD equal to least positive Am plus Bn equal to A alpha plus B beta equal to 1. So relatively prime means A alpha plus B beta is equal to 1 for some alpha beta. Now A alpha plus B beta is equal to 1 for some alpha beta means that A and B are relatively prime. So this is another consequence of not exactly Bezout identity, but the proof of Bezout identity that we saw in the last session. The next question we have actually seen in one of our previous sessions, but we will see that how to solve it using Bezout identity. If GCD of AB is D, where A and B are two positive integers, so that GCD of A by D and B by D equal to 1. This we have already seen, but we will try to see using the proof of Bezout identity. Now, GCD of AB is equal to D. GCD of AB equal to D implies there exists alpha, beta digits. This is Bezout identity such that A alpha plus B beta to D. Now we know that D divides A and D divides B, that we know. So if we divide D with both sides, A by D is an integer, D divides A, D divides B implies A by D an integer, B by D an integer. So there is no problem in writing A by D alpha plus B by D beta equal to 1. But A by D alpha plus B by D beta is equal to 1, as in the previous problem, implies that the GCD of A by D and B by D, that is the least possible positive linear combination of A by D and B by D. We already got the least possible number, that is 1. So the GCD of A by D and B by D is the least among A by D m plus B by D n, but least we have already got. No other linear combination can be less than this. Therefore, the GCD is going to be equal to 1. So if GCD of A and B is D, if we remove D from both these integers, then the remaining integers will have GCD equal to 1. Continuing with the applications of Bezout identity, we have the next question like this. If A and B are relatively prime, A and C are relatively prime, we have to verify that A and BC are also relatively prime. Okay, we have to show that the GCD of A and BC is 1. So for that, suppose that GCD of A and BC is D. Suppose D equal to GCD of A and BC. Therefore, D divides A and D divides BC. Since D divides BC, we can split D is equal to D1. So some part of D must be lying inside B and some part of D must be lying inside C. Therefore, we can write D equal to D1, D2, where D1 divides B, D2 divides C. For example, we have (12) divides 8 into 6. So from 12 we have 4 dividing 8 and 3 dividing 6. So we write 12 is equal to 4 into 3, where 4 divides 8, 3 divides 6. So this is our D1, this is our D2, something like this. So we split this D into D1, D2. Now D divides A and D equal to D1, D2 divides BC. Now note that D1 divides D implies D1 divides A also, because D divides A. So D1 divides A. Now D1 divides D implies, we have already seen, we have already written that D1 divides B. So this is not actually necessary. So this can be removed. So D1 divides A and D1 divides B. Therefore, GCD of AB is going to be greater than or equal to D1. Okay, but GCD of AB, we know that it's equal to 1. Therefore, D1 must be equal to 1. Since GCD of AB equal to 1, D1 must be equal to 1. Now, the same way, D2 divides D, D divides C, this is not correct. D2, this is not actually the correct thing to take. So we have previously D2 divides C, that is given. D2 divides C and D2 divides D and D divides A implies D2 divides A. Therefore, GCD of A and C must be greater than or equal to D2. So what we can say, GCD of AC is 1 implies D2 must be equal to 1. So D equal to D1, D2 equal to 1 into 1 is equal to 1. So what is the GCD of A and BC? Therefore GCD of A and BC is nothing but 1. So we established what we claimed. We have one more problem somewhat similar to what we have done, but in the next case we are going to use Bezout's identity itself instead of its proof. If A divides C and B divides C with GCD of BC, GCD of A and B relatively prime, then show that AB divides C. So A divides C and B divides C, but there is no common factor among A and B other than 1 itself. Therefore, the product AB also will divide C. This is what we are supposed to show. Okay, A divides C, it's given. So what is the consequence of this? What we can write in the terms of multiplicative notation. In multiplicative notation, we can write it as C is equal to A into some E1, where E1 is some integer. This is the meaning of saying A divides C. Now, B divides C in the similar way means C is equal to B into E2, where E2 belongs to Z. Now, a fact given is the GCD of A and B is 1. So, by Bezout's identity, we can write there exist alpha, beta integers such that A alpha plus B beta equal to 1. This is not. Now what we need is we need to show that C is a multiple of AB. So we need to connect AB and C. Here we have A, here we have B, but there is no C here, and there is no AB also. So suppose that we will try to bring C in this expression, A alpha plus B beta is equal to 1. Therefore A alpha plus B beta equal to 1. If we try to bring C, then we need to probably multiply C on both sides of this equation, giving C A alpha plus C B beta equal to C. Okay, now here we have CA, here we have CB. If we can show that the CA alpha is a multiple of AB, CB beta is a multiple of AB, then C also will become a multiple of AB. So we need to bring B here, already A is here. We need to bring A here, already B is here. So we have two expressions for C. One is C equal to A E1, other is C is equal to B E2. So if you use C is equal to A E1 here, you will be having A E1 A alpha, but we want B, not AA, but we want AB. So we will substitute B E2 here and A E1 here and C. Therefore A E1 A alpha plus B E2, sorry, exactly the opposite thing we wanted, not A E1, B E2 A alpha plus A E1 B beta equal to C. Now AB is here, AB is here also. So AB divides what are the parts? BE2 A alpha, BE2 A alpha, because A B is here, AB divides A E1 B beta. Together it implies that AB divides the sum, which is AB divides C. So we establish that if A and B independently divide C and A and B are relatively prime, then A and B collectively, that means the product A and B also will divide C. Such a similar technique we are going to use in the next problem. If A and B are relatively prime and A divides the product BC, so that A divides C. So we are going to make use of the basis identity once again here. So it's given that A and B have GCD equal to 1. Therefore, there exists alpha, beta integers such that A alpha plus B beta is 1. Now we need BC. So the best way to introduce C here or BC here is to multiply this equation on both sides with C. Therefore, CA alpha plus CB beta equal to C. Now it is given that A divides BC. So A divides this part. Now A divides CA. A divides CA and A divides CB implies that A divides the sum of A divides CA alpha, A divides CB beta, which implies A divides the sum also, and the sum is nothing but C. So A divides C, and that's what we wanted. We can have many more exercises in this way using which can be established using basis identity, but we are going to leave a few of them as exercises for you to solve, and we are going to discuss the concept of GCD of more than two numbers, which is an extension of the concept of GCD of two numbers. So the next topic is the following: GCD of more than two. So the definition is exactly the same as in the GCD of, as in the case of GCD of two numbers. So definition is the following. Let A1, A2, etc. AN be positive integers. D is the GCD of A1, 2, etc. AN if the following two conditions are satisfied. Condition number 1, D divides AI for I equal to 1 up to n. Second, if C divides AI for I from 1 to etc. n, then C is less than or equal to D. So these are the two conditions for the GCD of integers A1, A2, etc. up to AN to satisfy. So D we call as the GCD of these integers. So in the practical sense, how do we find the GCD? Let us see one example. Find the GCD of 12, 8, 28. So as in the case of the GCD of two integers, here also we have to find the set of all divisors of all these numbers. So what are the divisors of 12? 1, 2, 3, 4, 6, and 12. What are the divisors of 8? 1, 2, 4, 8. What about divisors of 28? 2, 4, 7, 14, 28. Now C 12, 8, 28, this is the intersection of D12, D8, D28. This is nothing but equal to 1, 2 is common. Now 4 is common. That's it. So GCD of 12, 8, 28 equal to largest element in C 12, 8 common divisors 28, that is equal to 4. So this is how we find the GCD of more than two integers. Just as in the case of GCD of two integers, we have to just take the set of all divisors of these integers and then take the set of all positive divisors actually, then take the intersection of these integers and take the largest among that. Next question probably arising is, can we have an expression similar to Bezout's identity in the case of GCD of more than two integers? The answer is yes, and to define, to make that statement, we should initially define what is meant by linear combination of n integers. So this is the definition. If a1 an are integers, then a linear combination of a1 etc. an is an integer a1 alpha 1, a2 alpha 2 plus etc. an alpha n, where alpha I are all integers. Now the general version of Bezout's identity is the following. If D equal to GCD of a1 an, then there exists m1, m2, mn integers, that D is equal to a1 m1 plus a n. This is the general version of Bezout's identity, and verifying this is not very difficult. We can verify it using exactly the same technique that we use in the case of the way in which we establish that there exists at least integer in the set of all linear combinations. That particular technique we can employ in this case also, and we are leaving this as an exercise. So this is exercise. We are going to see now that to find the GCD of multiple integers, we can break them into several steps in the following way. To find the GCD of A1, A2 and A3, we can find the GCD of A1 and A2, and then that GCD can be clubbed with A3 to find the GCD of all these three integers together. So the meaning of this is the following. If D equal to A1, A2, then GCD of A1, A2, 3 is nothing but GCD of D, A3. This is what we are saying here. Okay, to verify this, suppose that D dash is the GCD of A1, A2, A3, and suppose D double dash is the GCD of D, A3. To show that these two are the same, we will show that D dash is less than or equal to D double dash, and D double dash is less than or equal to D dash. Okay, now D double dash is the GCD of D and A3. D double dash divides D and D double dash divides A3, but D double dash divides D implies D divides A1, D divides A2. So D double dash divides A1 and D double dash divides A2 and D double dash divides A3. So D double dash divides A1, A2 and A3. Therefore, it must be it is a common divisor of A1, A2 and A3. Therefore, it is less than or equal to the greatest common divisor. Guys, D double dash is less than or equal to what is the GCD? That is D dash. So this is 1. Now we will show that D dash is less than or equal to D double dash. What is D dash? D dash is the GCD of A1, A2 and A3. D dash divides 1, D dash divides A2, D dash divides A3. So we are going to club these two. So D dash divides A1 and A2. We know that if D dash divides A1 and A2, by the alternate definition of GCD, we have seen that common divisor will divide the GCD. Therefore, D dash divides GCD of A1 and A2, D dash divides D3. What is GCD of A1 and A2? This is D, and D dash divides not D3, this is A3, sorry, A3. Now D dash divides D and D dash divides A3 means that D dash is less than or equal to the GCD of D and A3. But what is GCD of D and A3? GCD of D and A3 is D double dash. Therefore, D dash less than or equal to GCD of D, A3 equal to D double dash. So previously we have D double dash less than or equal to D dash. Now we have D dash less than or equal to D double dash. Therefore, D dash equal to double dash, or GCD of A1, A2, A3 is the same as GCD of A1, A2, and then take GCD of A3. So this is what we have established. A generalization of this statement I am leaving as an exercise, and the question is the following. If A1, A2, etc. An are positive integers, so that GCD of A1 to etc. AN is the same as A1 GCD of A1, A2, etc. AN minus 1, then N. That means find the GCD of all these n minus 1 integers, and if that GCD is D, then find the GCD of D and AN. That will give the GCD of all these integers. This is left as an exercise. We have seen a lot more consequences of the Bezos identity. We established several results, several interesting results as problems, and many of these results will be useful in our following sessions also. And we stop here. Thank you.